screen properly. Is this good?
Yes, yes.
Okay. So yeah, thanks again for the invitation. And so this is some work I've done with Tankut Khan and David Schwab, and it's on arXiv, but I think it should be out in PRX very soon if you want to take a look at the, so to speak, official version. And Tankut is at IAS in Princeton if you want to reach out to him for some questions about this as well. The thing I want to maybe start with is set the stage about the kind of recurrent networks I'll be talking about. And so here's an example of a classic RNN. And so it's described as a set of n coupled differential equations, which describe the evolution of the state hi. And Gij are the couplings between the different units. And typically H is some high dimensional vector. And the Gij, they couple the output of the internal state. So what I mean by that is there's usually some nonlinearity, which is saturating like a tan H, which transforms the internal state into the output of a neuron. And optionally, you might have some sort of an input to each unit. So this is the basic setup of the canonical RNNs. And they are very powerful models in modeling time series and solving tasks which have temporal components to them. In fact, the results that these classic RNNs, like I'm showing you, are Turing complete. They can basically implement arbitrarily complex computations. But in spite of this power, there are many issues with these classical RNNs, and a lot of them have to do with this specific feature of them, which is that the units interact with each other in an additive manner, meaning if you look at the equation of motion for, say, the unit I, what it does is it, in a leaky fashion, integrates the inputs from all other units weighted by the couplings. Now, these are problematic because for two reasons. One is that if you're thinking about this as a faithful model of real neural networks, we know that multiplicative interactions are quite ubiquitous, and from a practical perspective, it's known RNNs with these kind of purely additive interactions are very hard to train, especially when your tasks involve information on multiple timescales. And so for these reasons, these RNNs kind of fell out of favor for a long time in the machine learning community for more real-world tasks. But there's been a recent resurgence of RNNs for more complicated tasks. And the single reason that has sort of driven this resurgence is the introduction of this one feature, which is gating, which is a form of multiplicative interaction. And to be a little more specific, what I mean by gating in this context, I'm going to describe a couple of different forms. So let's go back to the RNN I was talking about. And now imagine that the output of neuron J, which is phi of Hj, is modulated by this dynamical quantity in the blue highlight, sigma of R. So what this kind of gating does is basically it acts as a dynamical modulation of the output of every neuron as time progresses. But you can also think about it as dynamical modulation of the columns of the coupling matrix. And another form of gating is where you have some quantity which dynamically modulates the integration rate as well. Now, if you go to the machine learning literature, people have tried many other forms of multiplicative interactions. And so why focus on these two? And maybe I'll give you a very short answer to that question, which is, one is empirical. What they've found is if you scour through the machine learning literature, it turns out like the forms of multiplicative interactions which actually matter as far as task performance are concerned usually end up being these two. One which modulates the integration rate, and one which modulates the output of the units. And there's also good biophysical reasons because these forms of multiplicative interactions are also ubiquitous in real neurons. And if someone is more interested by that, I can elaborate on that. And actually, I can't see any chats or faces, so maybe I should exit the full screen mode. Are people still able to see this?
Yes, we see well.
Okay. Okay, good. And so, okay, so these are the two forms of gating I'll be focusing on. And the one thing I want to mention is prior theory work has so far mostly focused on neural networks which have additive interaction. So here's a classical result going back to the work of Krishnamurthy, Somers, and Polinsky, where they were studying the RNN of the form I showed you before, with the couplings being independent random Gaussian entries. And what they found was a phase transition where if the variance of the coupling weights exceeded a certain value, then the network would show chaotic activity. Whereas if it was less than that value, the network just, the dynamics would flow to a fixed point. And this was a seminal work in the theoretical understanding of these RNNs. And there's been subsequent follow-up work, which has looked at various extensions to this. But without going into too many details, what I want to say is a lot of these extensions have the flavor of basically considering different random models for the GIJ. So for instance, there's this work by Nirav Stern where now the diagonal entries are much stronger. So they're order 1 instead of order 1 over square root n. But they are still within this universe of additive RNNs, the theoretical investigations. So even though gated RNNs empirically can do perform significantly better in real world tasks, it's not really understood why. And so this is the thing we embarked on, and we wanted to study what are the consequences of gating to dynamics and information processing capabilities of recurrent neural network. And to study this, we introduced a model which takes as the starting point the classical model, which is popular both in machine learning and neuroscience. This is the vanilla additive RNN. And then to this model, we introduced two gating variables, the update gate and the reset gate. So the quantities in the pink and the blue. And you can think about the update gate as a dynamical time constant. And it's something which varies between 0 and 1. And the reset gate is also a quantity which varies between 0 and 1, and it modulates the output of neuron J. And like I said before, you can also think about it as modulating the columns of J. And in the limit, these sigmas go to 1, the gates are open, we get back the dynamics of the classical RNN. So one more thing I should mention is the dynamics of the gating variables themselves. So Z and R are driven by the H variable. They don't have any explicit recurrence. They're driven by the H variables, but the coupling matrices which couple them to the H variable can be different. They don't have to be the same as the JH. So that's the basic model. And one thing I want to just mention is it's closely related to a discrete time model, which is popular in machine learning. It goes by the name of GRU, which is the gated recurrent unit. There are some differences, but it's very similar in flavor. So in this model, what are the parameters? the parameters are these three pairs of gains and biases. So there's a gain and bias for the nonlinearity phi, which takes the internal state of a neuron and converts it into some output. There's a gain and bias for the update gate, which is the gate which controls the time constant dynamically. And then there's a gain and bias for the reset gate, which is the gate which modulates the output of a neuron or modulates the columns of the connectivity matrix. And it'll turn out that these gains are actually important players in the behavior of the network. And what we want to know is, as you tune these knobs, what qualitatively different dynamics can you expect, and which of these might be beneficial or detrimental to information processing and learning. So this is the setup. And so maybe I should pause at this point and check if people have any questions. If not, should I go ahead?
I have one. The coupling matrices both in the two sigmas, they are random again as how do you choose?
Yeah, they are for the analysis I'm going to show you. They are JZ and JR are also IID random Gaussian. But for some of the results which will come up, the qualitative nature of the phase diagram remains the same, although the boundaries will change if you introduce some sort of elliptic ensemble here, for instance.
Okay, thank you.
Okay.
Okay, thank you.
Okay, so that's the basic model, and we want to know what happens to the qualitative dynamics as you change these parameters of the gates. And to give you, I'll first present a result which helps maybe anchor the remaining parts of the talk. And this is a phase diagram. And so this is a phase diagram in the alpha R and GH plane. And so let me remind you what these parameters are. Alpha R is the gain of the reset gate. So the reset gate, again, remember, is this sigma R in blue, and alpha R tells you how switch-like or binary this gate becomes. And it modulates the output of a neuron. And GH is the gain of this nonlinearity phi. So if GH is very large, the tan H will alternate between -1 and 1. And so the phase diagram I'm showing you is in the alpha R and GH plane. And when both of those quantities are low in this region 1 in blue, what you have is the network flows to fixed points. If you increase GH, what you get is a continuous transition to chaos. Whereas if you increase alpha R, which is the gain of the gate modulating the outputs, you get a very interesting discontinuous transition to chaos, which has interesting characteristics. And the gate which modulates the time constant enters in a very interesting way. And what it does is it can make all these regions, all the points in this thatched region, marginally stable. So that's a very, very super concise, high-level overview. And now the thing I want to do in the rest of the talk is maybe dig in deeper into each of these and talk about what the regions mean and what's going on. So let's do that. And so we'll start with how the gates shape the linearized dynamics, and then we'll see this interesting regime where you can get marginal stability in line attractors. And then we'll look at the Lyapunov behavior of the Lyapunov spectrum and how the gates shape the asymptotic behavior. And then there's this discontinuous chaotic transition I was talking about, and we'll dig into that. And the last part, which I'm actually quite interested in talking to you, is somewhat of an unfinished work, and maybe there's avenues to collaborate here, which is to think about mean field theory for gradients in these kind of RNNs. And so we can dwell on this later. And so I'm not sure if, depending on questions, how much of this I'll make through, but if you have questions, please feel free to interrupt, and I'm happy to spend more time in any particular part of this. Okay, so let's start with the local dynamics and how the gates shape them. And the way we study the local linearized dynamics is the state-to-state Jacobian. And in the gated RNN, the state-to-state Jacobian is a 3n by 3n matrix D, which has a block structure which consists of these random coupling matrices J and state vectors. And I don't particularly expect you to just look at this expression and understand how this came about, but the thing I want to illustrate is the block structure form of this Jacobian matrix. And the spectrum of this Jacobian will inform us about the linearized dynamics. And what we want to know is how the gates shape the spectrum. Okay. Since we are interested in studying large networks, we a priori expect that the spectrum will be self-averaging. And so we don't study a particular instantiation of a network. We look at the disordered average spectrum and post hoc verify that this is actually a valid approximation, meaning that the spectrum which you expect from averaging over J's is very close to the spectrum you get for any particular instantiation. And so this is the quantity we are going to study, this spectral density of the Jacobian. And the first equation is just the definition, and the second is an identity. And we can use techniques from random matrix theory to study this. The one technical aside I should mention, and maybe people know this here, is the Jacobian is not going to be Hermitian, so we have to use techniques which are suitable for non-Hermitian random matrices. And so what we do is, instead of studying a 3n by 3n matrix, we expand the phase space into a 6n dimensional matrix, and then in a certain limiting sense, we can get back the particular problem we wanted. Now, if you don't know about this, it doesn't matter. This is a technique which was introduced by Tony Z and Feinberg. I think there's also a nice exposition in this paper by Melig and Chucker. And the end result of this, when we try to calculate the spectrum, is we use the self-consistent Born approximation, where you get a set of closed equations involving basically 6 variables, which are traces over diagonal blocks. And what they let you do, amongst other things, is get the spectral curve. So which is the support of the spectrum in the complex plane. So it'll be all the complex numbers lambda which satisfy this equation. So this is the random matrix theory prediction for how the spectral support in the complex plane will look like. And the one thing maybe I should point out is, going back to why we wanted to do this, we want to know how the gates shape the spectrum, right? So the way that enters is all these averages I show you here. These are going to change as I tune those knobs in the gates, the parameters of the gates. And what we'd like to know is, as we do that, how will the spectral support change? How will the spectral density change? And so let's look at that and see if the RMT prediction actually is good enough. Yes.
Kamesh, can I ask you, because can you comment a bit on why the spectrum depends only on one-time quantities and not on two-time?
That's a very good point. So we wait. So these networks, when you start them, there'll be some transients, but they reach a time-varying steady state where correlation functions and even the responses are no longer dependent on, are basically in steady state. So if I sample the network state at one time, once it's reached steady state, and then do it some other time and look at the spectrum, it'll have the same form. So the spectrum reaches some limiting form.
Yes. So you assume that you are in the steady state and just everything is translational invariant. Yes,
that's the assumption. And empirically, if you want to know what that means, it means usually in these kind of networks, in a typical regime, you run it for something like 100 time constants.
Okay.
So related to this, the matrix that you are looking at, it depends on the state vector of the network itself. So on H, Z, and R variables. So the averages are over the stationary measure over those variables, right?
Yeah, that's a very good point. Right now, if you're just talking in the framework of random matrix theory, you can use the true state vectors, meaning the averages can be empirical averages, like in here, where you use this explicit average, but you can also do the following. You can say that maybe I can calculate these averages using mean field theory and see how the spectral curve looks. And the two agree very well in most of the regimes we care about.
Thank you.
Any other questions? Okay. Okay. So let's look at how the spectrum is shaped by the gates. And so the first thing I want to show you is, as you increase alpha R, so just a reminder, alpha R is this gain for the gate which modulates the output. So if you increase alpha R, what you're doing is you're making that more binary. And that gate you can also think about as a gate which modulates every column of the coupling matrix. So as alpha R increases, the modulation of the columns of the coupling matrix becomes more switch-like or binary. And if you increase alpha R, what we observe is that you end up increasing the spectral radius, which leads to instability. But there's something very interesting which happens when you increase alpha Z. So alpha Z is the gain for the gate which modulates the time constant. And so when you increase alpha Z, that gate is going to become binary, and the time constant, depending on the input of the gate, is going to flip from small values to large values, and this happens dynamically. Now, when you increase alpha Z, I want you to focus on the panels A and C. Something very interesting happens. So two things. One is that the spectral curve gets pinched at 0 or close to 0. And then there is a accumulation of eigenvalues close to 0. And this pinching reduces the number of unstable directions, and it drastically stabilizes dynamics. And in the limit, it can lead to a very interesting phenomena of marginal stability. And that's what I want to maybe dig into a little deeper right now. So yeah, going back to that picture, you take a spectrum of a network, which technically on the left is in steady state, but it's a time-varying steady state, and the network is unstable. But you increase alpha Z, what happens is you end up with a spectral curve which gets pinched at 0, and then accumulation of eigenvalues at 0. And in the limit that alpha Z becomes infinity, it can make this previously unstable system marginally stable by poising the spectral edge exactly at 0. And when will this happen? So this will happen for all points in this thatched region. So if you choose parameters from these points in the thatched region, you're going to have a network which is initially unstable, but then if you make the time constant gate more and more sensitive in the limit, you're going to approach, you're going to make that unstable system marginally stable. And in the marginally stable state, the spectral curve will rest on 0, and you'll have an extensive number of eigenvalues precisely at 0. And this is kind of quite interesting because you don't need, there's a very large parameter regime which allows you to do this, unlike previous examples. Usually for marginal stability, you have to be at a bifurcation point and fine-tune things. But here you have this wide range of the space where you're able to achieve it. Now, this has functional consequences because in this marginally stable regime, you can get line attractor dynamics and very long timescales. And maybe I think it's useful to talk more about the line attractor dynamics, which is, if people haven't heard it before, the idea is you want dynamics such that there are some regions in the phase space along which some directions in the phase space where perturbations are maintained. So perturbations to the system are retained in the state of the system as a memory, but perturbations along other directions decay away rapidly. And you can clearly understand why this is useful for memory. And most ways of achieving this have required really fine-tuning parameters or handcrafting the connectivity matrix. And here you kind of generically get this in this marginally stable regime. And here's an example of what I actually mean by the system functioning as a line attractor. So what I'm showing you is a network in this regime where alpha z is large. So you get this pinching of the spectral curve and the clumping of the eigenvalues at 0. And actually, the reason I'm showing you the Jacobian here is the system doesn't even have to be technically marginally stable. Here it's actually unstable, but the fact that the spectral curve pinches suppresses many of the unstable directions. So even though the system is technically unstable, you have access to this slow dynamics and line attractor function. And what I'm showing you here is to a system in this state, you apply an input between these vertical dashed lines. So for, I don't know, maybe 10 units of time. And if that input is aligned to the slow modes, then the system will integrate it and retain it in memory for a long time after the input is gone. And if it's off the manifold, then the perturbation will decay away very rapidly. So it's a very useful network as an integrator. And again, the emergence of this doesn't require any fine-tuning of the gains or any special form of the J matrices, which was a significant limitation in previous approaches. It's also interesting in machine learning RNNs, when people train gated RNNs on certain tasks which involve long timescales and information over many timescales. And then they see that what is the solution that the network has found. What they observe is something which shows evidence of line attractor dynamics, meaning after training, there's some geometric object in the phase space that the network creates where inputs can move the state on that object. Inputs of that object will decay away rapidly back to that attractor. So this was an empirical observation, and so maybe this theory gives some idea of how gating can actually produce this. Yeah.
I didn't get how the can you see how the point in the phase space where you are shape this geometric object, like this line attractor, or how it changes by there is a whole region when this holds, like right?
Yes, that's correct.
But then within this region, does it change particularly, like what are the inputs that are integrated, or it doesn't change?
Yeah, you're talking about the particular shape of the attractor.
Yes.
Yes. Okay. So it turns out in this particular paper, all we knew was there was marginal stability. But then once we started exploring how it comes about and what is the shape of the attractor, it turns out it actually is by a principle which is more general than just gated networks. And the line attractors have a very complicated and interesting shape in the phase space as union of sheets which are joined together. You have some control over how you can shape them, but we wrote up a separate smaller paper on that. And
is it online?
Yeah, it's a version of that is in archive right now. It's called Emergence of Memory Manifolds, and maybe people are interested in that. But when we were writing up this paper, we didn't exactly know. We knew that marginal stability emerged, but how the mechanism of how it emerged and the nature of the geometric object wasn't entirely clear at that point. And once we dug in, it actually turns out to be very rich and complicated. And maybe this is something we can discuss. Okay. The next thing I want to maybe very briefly talk about, since we're kind of close to half time, is the asymptotic behavior of the network, because till now I was telling you about more of the linearized dynamics. And the way we look at the asymptotic behavior is through the Lyapunov spectrum. And so the Lyapunov exponents tell you how small perturbations will grow or decay with characteristic exponents. If you're curious how we calculate this, there are many numerical subtleties to get this. So we use a particular thing called the Iterated Qr Method. And the upshot of this is particularly this plot. What I'm showing you is the top 50 Lyapunov exponents in a large network. And I want to show you how these exponents are shaped as you tune the gates. So on the top, you see that as you increase alpha z, so alpha z is the gate which controls the time constant. And so higher alpha z means that gate becomes more switch-like. And what we saw before is this is the particular gate which leads to slow dynamics and marginal stability. And that was a local statement, but the thing which is nice is it's also confirmed in the asymptotic behavior that it flattens the Lyapunov spectrum. And similarly with alpha r, which is the gain of the gate which modulates the output, we saw that higher alpha r led to instability. And here we also see that the entire Lyapunov spectrum gets lifted as you increase alpha r. So this is a good verification of that behavior, local behavior, and that it holds asymptotically as well. So this is a numerical study of the asymptotic behavior, but we can also look at asymptotic behavior through analytics or some aspects of it. And the tool we use to do that is the dynamical mean field theory, which maybe people here are experts on. In the mean field picture of the dynamics, we have basically two order parameters, which are depend on time, and they're the population averaged means and the response functions. And the picture which emerges in the mean field is the 3n dimensional deterministic coupled differential equations are now reduced to 3 stochastic differential equations, which are driven by noise processes which have to be computed self-consistently. And you can numerically do this using a method which was proposed by Felix Roy and Giulio Baroli and colleagues. But I want to mention one thing is this Z-gate renders the H variable in the mean field picture non-Gaussian. And so finding a fully closed form solution in the regime of finite alpha Z is actually analytically intractable. So you can do it using this numerical technique. And since the numerics match the full network simulation, what it means is the numerical picture is, the mean field picture is accurate, but nonetheless, you can't really solve the mean field equations in closed form for finite alpha Z. But nonetheless, it's still useful to have this mean field picture because it allows you to study the role of the R gate. And the particular thing we use it for is to calculate the Lyapunov exponent. And maybe I should say just a word about how we do that.
Sorry, Kamesh, can I ask you another thing on this?
Yes, please. Go ahead.
So here in the DMFT, when you solve the DMFT, are you solving it in the stationary state or for the full dynamics? Because before there were 2 times, right, in the equations that you wrote.
Yes, there were 2 times, but in the actual solution, like you can see over here, there's only 1 tau.
I see.
So we are solving it in steady state.
I see. Okay.
Most of the analysis here is going to be in steady state, except for the thing at the very end, which will be about gradients, and that is very incomplete, and that's where maybe I want to maybe throw out some things which could be possible collaborations. Yeah. So we can use the DMFT to study the long-time behavior by using it to measure the maximal Lyapunov exponent. And this is a method which was developed by Derrida and colleagues, but also very nicely explained in a paper by Moritz Helias. And so the idea is you create 2 systems which have slightly different initial conditions, and then you study the generating functional of the combined system, and the interreplica correlation function will give you information about how perturbations grow and decay. And the end result of all this is you end up with this complicated looking equation, which I don't want you to try to make sense of, but what it basically gives you is an eigenvalue problem. And the solutions to this eigenvalue problem are the maximal Lyapunov exponents. And you can see that in this particular case, the numerically calculated maximal Lyapunov exponents line up quite well with the DMFT prediction. And again, like I mentioned, the DMFT is useful to study the role of the R gate, but the DMFT is not tractable when you have finite values of alpha Z. So the time constant gate has to be set to basically removed from this picture, from this analysis. There is an interesting phenomena here, which I want to maybe touch upon, which is for the lower values of alpha R, there is a transition to chaos, which is continuous, and the Lyapunov exponent increases and continuously goes above 0. But when alpha R, which is the gain of the output gate, is large, what happens is as you increase GH, you get a discontinuous transition where a stable system abruptly goes to strongly chaotic activity. And there's some very interesting features of this discontinuous transition. And that's something I want to maybe dig into a little bit deeper now. And to explain some features of that transition, so this is the actor we are going to focus on, this R gate, which modulates the output. And alpha R is the gain of the sigmoid. So as alpha R increases, the sigmoid becomes more binary or step-like. And what we saw is as it does that, the network exhibits a transition to chaos, which is discontinuous. And that has some, I think, interesting properties. And one way to look at it is we start with just the pure mean field, not even the dynamical mean field, but just the mean field picture of what's going on. So the mean field equations are given below here, and we can solve them in the stable regime, and the plot on the left shows you the solutions. So in the stable regime, all the network should do, say for GH is 1.8, is the network should go to a fixed point. And that fixed point is 0. That's the stable solution. So the only solutions which you should expect for delta H are 0. But there's something interesting which happens, which is in this regime, when you increase the gain of the output gate, alpha R, 2 non-zero solutions spontaneously appear. And what does it mean? And so what it means is there are solutions in the phase space which are consistent with this mean field solution. Now, intuitively, we first assume that what this corresponds to is when alpha R increases beyond this value, you now get many, many, many unstable fixed points in the phase space. But again, this is a mean field description, and going from mean field to microscopic dynamics can be tricky. So we got pushed by a reviewer, but if you do a kind of Katz-Rice analysis, you actually can argue that what's going on when you get these two spontaneous solutions to the mean field solutions is also a situation where you go from only the 0 fixed point in the phase space being stable and being and appearing to many, many proliferation of unstable fixed points in the phase space. And if you plot this critical line in the GH and alpha R plane, this is how it looks. So one thing I want to point out is we are still very much in the stable regime, meaning in these values of GH, if alpha R was 0 or small, all the network would have done was that thing in the blue region of the phase diagram. It would have just gone to the 0 fixed point. But the moment you increase alpha R above a certain value, now you have these spontaneous solutions to the mean field solution, which corresponds to an explosion of critical points in the phase space. But the critical points don't have any obvious dynamical signatures, meaning if you look at transients before and after the transition, you won't be able to spot them. It's only when you increase the gain beyond a second critical value that you start seeing chaotic dynamics. And the reason I'm maybe emphasizing this so much is this stands in contrast to some classical results for additive RNNs from Wainrib and Touboul, where what they observed was the appearance of chaotic dynamics was very strongly tied to proliferation of critical points in the phase space. And so this is a plot from their paper where they're plotting the explosion of the critical points on the x-axis and the Lyapunov exponent on the y-axis, and these two are quite tightly linked. So in networks with multiplicative interactions, it seems like these two transitions become decoupled. And so to summarize that picture more intuitively, I'm going to go back to this phase diagram and describe there what happens. So in region 1, the only thing you have is a fixed point, and that's the global attractor of the dynamics. If you increase alpha R, which is the gain of the gate modulating the output, then you get to region 2, where the fixed point is still the global attractor of the dynamics, but now you have an explosion, a proliferation of unstable fixed points. Now, if you increase alpha R beyond a second value, you go into region 3, where you start seeing chaotic dynamics, but the fixed point is still stable. So there's a coexistence of a pseudo-attractor, chaotic pseudo-attractor, with the with the stable fixed point. It's a very interesting regime which we are trying to characterize. It goes by the name of repellers in some literature. But here what you'll notice is transients will be chaotic, but then they'll eventually die into the fixed point. And these transients will scale with the system size. And once you increase GH, what happens is you move from left to right, and you kill the fixed point, and the only thing that remains is the chaotic attractor. One consequence of this transition, for people who are maybe somewhat more familiar with the neuroscience literature, is it challenges some of the dogma of the role of inputs. And what I mean by that is the following. Because of this discontinuous transition, you can have a situation where external inputs can drive chaos. And this is static external inputs can drive chaos. And this is interesting because traditionally in these large random networks, when you apply external input, either periodic or static, they mostly have a role of stabilizing the network, and they move the transition to chaos farther away. And so many people, Haim Polinsky and also Moritz Elias and others, have written about how stimulus or input suppresses chaos. But when you have multiplicative interactions, we see two very different kind of behaviors. So that's shown in these plots, where in certain regimes, you can have input doing the classical role of suppressing chaos. But in other regimes, what will happen is you can be in this blue region where the system is totally stable. So that's the top left plot. All the system does is it goes to the zero fixed point, and then you apply static inputs in that region, and the network, a fully stable network with static inputs, is pushed into strongly chaotic activity. So multiplicative interactions can give you this induction of chaos for non-time varying inputs. So yeah, just wanted to, this is maybe tying to some more tangential neuroscience and machine learning literature which studies the role of inputs. The last thing I want to maybe do is shift gears, and this is the part where things are a little more incomplete. And so maybe I should just pause here, and before I go into this, see if people have any specific questions or clarifications they would like to. If not, then yeah, sorry. Yeah.
Can you just remake a summary of the properties of those phases? In particular, I didn't understand the one in which you have an attractor and some chaotic phase, but it is just intermediate in time. Can you just explain again?
Yeah, so I can explain. Yeah. So what we see is in this phase, region 3, basically, if you start close to zero, let's say a finite distance away from zero, but small distance, the network will flow to the zero fixed point. If you start away from that, then you will get chaotic transients. And the reason you know they are chaotic is if you take large networks and numerically measure the Lyapunov exponents, they are actually positive. But what will happen is after these chaotic transients, you will eventually hit the basin of the zero fixed point and go to the zero fixed point. But as you increase the size of the system, the time to do this is going to scale with that. So the transients will scale with the system size. So in the infinite system limit, you're in this very weird place where there's a hole in the phase space with a finite basin of attraction. And there's a chaotic pseudo attractor on which if you start, you'll be there forever. But if you touch the basin, then you'll go into the basin.
Okay. Thank you. Thank you.
Yeah, was there any other question?
Yeah, I was just confused because alpha R, I got what it is, I think. So it seems to say that to see these features, you need very like switch-like columns in the J, right? Because it's called Y, the value.
Yeah, so you need the gate to be somewhat switch-like, and the gate multiplies the columns of J. But the one thing you have to be careful about is the gate, the output of the gate is a value of the gain multiplied by the activations. And the activations are generically Gaussian centered at 0. So even if the gate gain is high, the product will have the product of the gain and the activations can have a different distribution. You can still have order 1 values.
I see. But so because this the other parameter that is basically the time rescaling is not the Z is not appearing in the phase diagram. Is it? I don't remember if it's related to the GH or I think I forgot.
I know it's alpha Z. So that's a good point, and maybe I should point this out. The lines in the phase diagram are mostly decided by alpha R and GH. But the way the alpha Z, which is the time constant gate, comes in is this dashed region. What it does is it takes previously unstable states, and if you make the time constant gate switch-like, all the points in this dashed region can now become marginally stable.
That's the pinching that we have seen at the beginning.
Yeah.
And what is the GH? Then I don't remember.
Right, GH is so remember in the neural network, the H variable was passed through a nonlinearity phi.
Yes.
And the phi is some nonlinearity like a tan H. So GH is the gain of that. If GH is low, then the tan H is going to be very linear, and if GH is very high, then it's like a kind of a Ising kind of limit, where you get -1 + 1 as the outputs.
Thank you.
Okay. Okay, so this was all mostly about like what the gates do and explaining the phase diagram. The next part is going to be a little bit speculative, and I'm running a little bit out of time, but let me just proceed and see if people have ideas, because this is also the more incomplete and maybe parts where maybe there's avenues to discuss things. And what we want to do is maybe try to come up with a DMFT for gradients, gradients within dynamical systems. And so the starting point is this framework, which was laid out by Pontryagin and colleagues in the control theory literature, where you start with a dynamical system, very generally described by this equation H is equal to 0. So if you wanted to think about the gated network, then X would be this tuple HC and R. But it doesn't have to be that. And theta are the parameters of the dynamical system. And then you have some sort of a loss functional, which takes a trajectory generated by the dynamical system and spits out a scalar. For instance, it might be something which tells you, I want my dynamical system to generate certain trajectories. How far is the true trajectory from the target trajectory? Okay, so then you might want to have something like a mean square loss. And what you want to do is calculate what is the gradient of this loss or cost with respect to the parameters. And that becomes really tricky because as you wiggle the parameters, the trajectories will wiggle. And so calculating this can be complicated. And so the nice thing introduced by Pontryagin was a clever use of Lagrange multipliers, where what you do is the following. You introduce an auxiliary variable lambda, which has linear dynamics. And then you have a way of calculating the gradient by doing the following. You run the forward dynamics to get the trajectories x. Then you start from the end of the time and get the values for lambda, solve for lambda, and the dynamics of lambda are governed by the same Jacobian which we were studying before, but the transpose of it, and hence the name adjoint, adjoint formalism. So once you get the forward trajectory, you solve for the reverse trajectory, and once you have the forward and the reverse trajectory of the auxiliary variable, the gradient is given by this equation over here. Okay, so that's the adjoint formalism, and I want to make a few comments. One is, at this point, the system doesn't have to be high dimensional. It doesn't have to be disordered. There's no randomness. This is very broadly applicable. The second comment is, the gradients are governed by lambda. And if you look at the expression for the gradient, a usual problem when you train recurrent neural networks is that the gradients explode or vanish. Now, if you look at this, the only term which is not well behaved in this expression for the gradient is lambda. If lambda explodes or vanishes, then you have a problem. And the thing dictating whether lambda will explode or vanish is precisely the state-to-state Jacobian which we were studying before. So it gives a fine-grained perspective of this observation that it's always better to train networks at the edge of critical points. And that's because the gradients will be well-tamed. And that's because the Jacobian will be well-behaved. And as we saw, the behavior of the Jacobian is also consistent with the asymptotic behavior. So lambda will be well-behaved close to critical points, and gradients will hence be well-behaved. And as an aside, it also is interesting because it very concretely ties forward dynamics to what you can learn from gradients. So, what the network can do in its forward dynamics very strongly constrains what the network can learn using gradients in some sense. So all this was general. Where does DMFT come into all this? And the thing I want to say is, if we have a large disordered dynamical system, then you can start to think about a combined DMFT for both lambda and x. So a combined DMFT for the forward dynamics and the gradients, and the auxiliary variable describing the gradients. And for the vanilla RNN, it takes the form something like this. Maybe the precise expressions are not that important, but you have a STE for H, you have an STE for lambda. Now you have to care both about the two-time arguments instead of just the stationary state treatment, which we did for the forward dynamics. And in this kind of a DMFT picture, one of the things you can use it to calculate is things like mean square value of gradients across the whole phase diagram. So if you're able to calculate C phi and C lambda, then you can use integrals of this form to get some Frobenius norm of the gradients, which will tell you what are regions in which gradients will blow up or die down. And you can sort of extend this to the gated RNN. The expressions look much more complicated, but the basic idea is the same. And so I wanted to mention this because I think maybe there's some promise in this direction of combining this adjoint formalism with the DMFT framework to analytically study gradients in RNNs. But we, for interest of time and also limited resources, have sort of left it at this point, and there's more scope to expand, and I'd be very happy to talk to you about this. And with that, I'm a little over time, and I should probably end. We looked at how gates influence the dynamics of a recurrent neural network, and two interesting phenomena which came up were this emergence of marginal stability and line attractors over a very wide range of parameters. and this chaotic transition where dynamical and topological complexity are decoupled from each other. And the chaotic transition also leads to this phenomena where stable static inputs can push a completely stable system into strong chaotic activity. So that's a quick summary of the whole thing, and maybe I'll stop and ask questions now.
Okay, thank you, Kamesh. Thank you.
Yeah.
So, are there questions? We asked a lot already, but just unmute yourself. Yes, there is something in the chat. Okay, there is Valentina that is asking something in the chat.
I missed something on phase 2. Am I correct? I found one stable. Okay. This is a good question. Let me just reiterate the question to maybe people who are not able to see the chat, or maybe everyone can. So what Valentina, I think, is asking is, okay, you get these unstable fixed points in the phase space, but how is it that you do not see any dynamical signatures? Now, it is true that if all these unstable fixed points show up in the phase space, then they should affect the dynamics. And maybe there's a way to probe them that you'll actually see the effect of the unstable fixed points on the dynamics. The only thing we want to say is, if you just look at transients, meaning if I start the network from different initial conditions and see how it goes to the fixed point, the time of the transient doesn't show any signature of the unstable fixed points. If I just showed you the transient, looking at that, you will not be able to tell me which side of transition 2 you're on. Now, there may be other clever ways of probing the phase space where signatures of this unstable fixed point stand out, but we did not manage to find them. Now, you might also be curious, are there actually truly unstable fixed points? You can numerically actually try to find those unstable fixed points and start at that, and it turns out it actually truly is an unstable fixed point. Yeah, so that's the short answer to your question. I don't know if it answered it. Let me know.
Okay. Are there other questions? Actually, I have a few on the these things, so probably it's fine. So I have a question on the very last part on the gradients.
Yes.
So if I understand correctly, so you want to find the theta variables, right? So this is dynamical system, then you get some kind of optimal control, which is Poitras in principle. So you should get some backward equation. Is this the equation for lambda or not?
The equation for lambda is actually you start at the end and then
backward.
Yeah, the initial condition is lambda at the end is 0. So let's say you're observing a time interval 0 to capital T.
Okay.
And then you get this backward equation. You're right. And so, so you solve for the forward x, and you solve the backward equation. And once you have lambda and x, then the gradient is given by this sum or integral on the top.
But in principle, then you may write a kind of Fokker-Planck equation for lambda, or not? Sorry, not for lambda, for x. So in principle, you have a backward equation that tells you your control.
Yeah.
And then the forward equation you control with the MFT.
Yeah, and so let me maybe bring that up. This is kind of how the DMF description will look.
Okay, I see. And then you have it self-consistently. I see.
And we didn't push too much towards solving this, but I think maybe it's, at least for the vanilla RNN, it might be tractable.
Well, I mean, numerically, you can do as for, as for because this is, I mean, it's like the MFT, except that you need to have a guess for C lambda. So you start with a guess for C lambda and C phi, and then you can integrate the two. I mean, I don't know how much it's stable, but it can be done, like Hopper, like what was done by Hopper.
Right. There's the source term, which I think is mostly okay, but shouldn't be this gradient, this f term. That comes from the cost function, but I think that's not a big complication.
But F, you know.
F we know.
So in principle, this is because in general, when you have this optimal control stuff, you have. I mean, here you reduce the equations to ODEs, while in general you have PDEs because you have the equation, the Bellman equation. But here you use the trick to go to lambda, to use the lambda. So in principle, it could be. I mean, it should go to an attractor, this self-consistent dynamics. Okay, I see. And okay, and then I have also another question. It was on the alpha Z. So, so I mean, as far as I understand, the fact that it becomes more switch variable, the sigma Z. What does it mean? It means that if it is 0, essentially you freeze the dynamics.
If it is 0, then actually no. If it is 0, then let me bring up the equation again. So if it's 0, it's actually you're getting closer to the vanilla RNN, right? So if it's 0, then sigma Z is half.
No. If it's sorry, not 0, but if it's where should I go? I mean, essentially sigma Z is between 0 and 1, right?
Yes.
So if sigma Z is 0, essentially you are freezing the dynamics. Because
okay, but that would mean that the argument of the sigmoid is negative.
Yeah. So I'm just thinking about, and instead if it goes to 1, okay, it's not very fast dynamic.
But what if the alpha Z goes to infinity? Doesn't this become a switch?
Yeah, if alpha Z goes to infinity, then it becomes switch-like. But what's important is which sigma Zi is 0 and which sigma Zi is 1 is not fixed. You see what I mean? Like if I move the state somewhere else,
not everybody that is freeze.
Yeah, which population freeze, which population does, then that's not fixed.
Okay. I need to think a bit more about that. So
actually, yeah, I want to maybe post something which might be of relevance. We probed a little more into this phenomenon, and it turns out there's actually quite a lot of very interesting stuff which comes out. And so maybe.
Okay. Yeah, let me open it so that I'll remember. Okay, maybe, I mean, if there are people that want to leave, maybe we can close and continue the discussion. If there are no other questions.
Me, I would like to ask one question.
Please go, Antonio.
Yes, it's about phase 2, where there is the decoupling between the dynamics and the topological complexity. It was a bit puzzled by this fact. You said that if you run the dynamics, basically you see no signature in the transients, right?
Only in the transients, yes.
Okay, but so I mean, this doesn't depend on the initial condition. Like I don't know, if you start the dynamics very close to one of those critical points, maybe you will see something.
Yeah, that's right. So we So the only variations we did were different distributions for the initial conditions. Now, finding critical points and running dynamics close to them, I think will maybe give you something, but we didn't explore that fully. And this kind of relates to Valentina's question, which is, if you get critical points and you know that critical points come in phase space, which we know by numerics, they must have some signature in the dynamics. I mean, otherwise it's kind of weird. But I guess what we are saying is, if you just sample initial conditions randomly in some sphere or cube or some other distribution, the time scale of the transients doesn't give you any information about these critical points.
I see. So basically, it's basically the typical dynamics that I get from the MFT doesn't see the presence of these critical points, but maybe there can be fluctuations around these dynamics that do feel that these critical points.
Perhaps. And maybe one reason why we found it surprising is in additive RNNs, this is very much not the case.
Mm-hmm. I see. Thank you.
Okay, are there other questions? Okay, so if not, thank you, Kamesh, again. I stopped the recording.
Thank you. Yeah.